and we're gonna start this lecture. So this is our second lecture from Stefan Zellner-Rembold from Manchester, who's gonna continue to enlighten us about neutrinos. So Stefan, it's all yours.
Thank you. I'm just trying to share the slides. That's okay. You should see the title slide.
Yeah, all good.
Okay. So let me just continue today with what we where we finished off yesterday, and continue with our program of understanding neutrino interactions and physics at accelerators. And where we left off is shown on this slide. We defined the PMNS matrix, which describes the mixing of and oscillations of neutrinos of three different types of flavor. The way the matrix was decomposed, can you see the pointer moving? Yeah.
Yes, we see it.
Yeah. So the solar, so the way it was decomposed is that we have this part of the matrix, which is the mixing between the first and second mass eigenstates, and then this one, which is between the second and third. This is often called the solar part because that's where, you know, this is the part of the matrix which dominates for solar oscillation. This one is often called the atmospheric part of the matrix because it is dominated by atmospheric oscillations. The one we haven't looked at in detail so much is the part in the middle. Now, this one is actually very interesting, even though it is expected to be small, because we see here this phase delta, which is, you know, the ultimate prize. We want to understand CP violation, but in order to do that, we have to be able to measure this term, which requires that this factor in front of it is definitely not zero. From the measurements we have done so far in the solar and atmospheric sector, we see that these angles are quite large, and the mixing between the states is quite significant, and you can see that on this plot, which shows the mass eigenstates for the normal hierarchy, or I sometimes use the word ordering. There's a little bit of a you know, people use both terms, ordering and hierarchy. It's probably better to call it ordering, where 1, 2, and 3 follow that sequence. And you see that here the mixing is actually quite democratic, if you want. You know, the three flavors contribute equally to nu2, for example. This this term, however, is expected, as I said, to be small, and one way we can see it is looking for nu-e mixing driven by this mixing by this mass difference. So you see there's a very small component of nu-e in here, and what's driving this is this mass difference, and therefore you know, the oscillations driven by this particular frequency. The way to do this, to look for nu-e mixing, is we should start with nu-e in some form, and as we have seen, the best way to do this is from a reactor, where the nu-e's are produced, or actually better, the anti-nu-e's in the reactor from beta decays. And one of the experiments that does this is the Daya Bay reactor experiment in China. It's located close to Hong Kong, just across the border into China, next to a big set of power plants, which are here. And then there are different sets of several detectors here nearby to the reactor and a little further away. And that you do because in order to see the oscillation effect, you want to have a detector close by to the source and then further away so that you can normalize the two things. This is shown in a more quantitative way here. This is the so-called survival probability, so the probability that the anti-nu E coming out of the reactor stays an anti-nu E as a function of the distance for typical energy, which is of the order 3 MeV when it comes out of the reactor. And you see the total mixing you expect with the oscillatory behavior, and here at the short distances compared to so compared to a survival probability of 1, you see this effect of the red curve, which is exactly the mixing driven by this angle theta 1,3. The oscillations driven by this angle theta 1,3 and this mass difference squared, this frequency of delta, the larger one, the atmospheric one. So if you want to build an experiment, then what we can do, and this is what Diabe has done, we look at the pretty close. So and this is actually shifted. That's a PowerPoint effect. It should be more on the left. For some reason, it's shifted over. So we built a detector here, and then we built a detector here, and we compare the anti-nu E flux, and from that you can then derive this angle theta 1,3. Again, this I've shown before. This is the layout, and you have a hole which is about 300 meters from the reactor, and then one which is like 2 kilometers away. The way the detector works is this is a scintillator detector, which is loaded with gadolinium. You often do that in order to get high neutron capture cross sections. This is because the process we are looking for is inverse beta decay, as it is shown here. So the anti-nu E hits a proton, and the reaction produces a neutron and a positron. The positron annihilates to a gamma and a pair, and the neutron is captured, emits photons, which are then all recorded in the detector, in the scintillator detector with photomultiplier tubes. And there are 8 of these detectors, which are all about 20 tons. Now, this is only one of those experiments. There was quite and I'll not talk about the others in detail, but there are others, Double Show, Diabe, and Reno, where the experiment that did this, and this was about 10 years ago. So this is in France, Double Shows, and Diabe is in China, and Reno is in Korea. And they all did a similar measurement, which is comparing the rate of antineutrinos at their far and at their near hole. And you see that there is a depletion, and this depletion can be described by theta 1,3, and you get actually very precise measurements out of this. So the surprise, so it's this term here is of the order 0.1, and that was actually larger than what people expected, and it was good news for potential CP violation measurements, because that means that the term in front of the delta is actually not that small. There's somebody cutting the grass outside, so I hope you don't hear that. So this was good news and an exciting measurement. And you see that now these experiments have progressed. This is a relatively recent measurement from I think Neutrino 2020. And on the right side, you see exactly what we talked about before. The no oscillation curve is shown here. And then the measurement of the prediction for a weighted baseline, which is like 500 meters and like 1.6 kilometers, and you see how that depletion works. An interesting aside for this is that it's actually not been so easy to understand the flux from a reactor. That's the disadvantage when you work with a reactor compared to an accelerator. A reactor, of course, is an extremely complex machinery, and the process of burning the fuel is very complicated. And all these experiments observed unexpected bumps in their spectrum, which could actually be attributed to nuclear reactions in the reactor, which hadn't been fully understood. So this is just an interesting aside. So we now know this term isn't too small. We have measured this with reactor anti-nu E disappearance. Actually, another way of looking at this term is to look at nu E appearance in a nu mu beam, because there should be a small component of this in a muon neutrino beam. Again, this component is small, and if you do that, you would be sensitive to measure this to θ13 and the phase. And one of the challenges will be to disentangle, if you measure this part of the matrix, the two effects. And that's what we'll talk about in the rest of this lecture. Let me just remind you in very general terms, you all have heard, I assume, about the CKM matrix, which describes mixing in the quark sector. And it's, of course, a very similar matrix in principle. However, if we now look what we learned about the PMNS matrix and the size of these terms in this matrix and compare this to the CKM matrix, we see that the CKM matrix between the three quark flavors and the PMNS matrix between the three neutrino flavors it's quite different. The CKM matrix is mainly diagonal, and the off-diagonal terms are really small. The neutrino matrix looks much more democratic or uniform. Now, this is an interesting observation. We don't really understand, but it could be some underlying symmetry, and it just shows you that neutrinos behave quite differently. Now, let me just quickly talk about a little bit motivate the CP violation measurement. We all know about matter and antimatter. This goes back to now almost 100 years, and Paul Dirac that predicted for fermions that you would see antiparticle states. And the first anti-fermion was discovered, the positron, by Anderson in 1932 in cosmic rays, and you see actually the entering positron and the exiting positron. You know this because there's a lead plate and it's lost some energy, so you know the curvature from that. And this was positive proof that these anti-particles exist. We also know that there is, assuming there was a symmetry at the beginning of the universe, we now live in a universe where there's fortunately some asymmetry between particle and antiparticles. However, that's why we're here and can discuss all this. However, the asymmetry that you need at the beginning and at the Big Bang to explain this is actually relatively small. It's a small effect. So this is important because one of the conditions for this asymmetry to exist is the violation of CP symmetry, which I've just quickly sketched on the right. What it means is C stands for charge, parity P stands for parity. And basically what it means, you turn around the charge of a particle, and in terms of its spin, you make a left-handed particle, a right-handed particle. So that's how you get, like, say, from an electron to a positron. Now, the violation of this CP symmetry is important because it is one of the Sakharov conditions. And just as an aside, Sakharov, is shown on this picture here, was born almost to the day 100 years ago. So there are some celebrations actually happening this week. And those three conditions are: there's baryon number violation, there's CP violation, and there's a departure from thermal equilibrium. And that's why we are so excited and interested in measuring this CP violation, and both in the quark sector, but where it's been observed, but also in the lepton sector, which is what we are doing here. One of the exciting and interesting thing about it is that it could lend support to the theory of leptogenesis, which is one of the ways to explain this matter symmetry in the universe. So let me just say a few more words about this. We have this PMNS matrix, which is a 3x3 matrix. And while a 2x2 matrix, which we started out with, is real, these matrices are in general imaginary due to this phase delta. And the interesting bit is that CP violation, which is the difference between a process and its CP conjugate, is actually only possible when the matrix is imaginary, because it creates a difference between a process going in one direction and going in the other direction, and that requires that we have at least 3 generations. Of course, the same is true for the CKM matrix, where we have observed CP violation in quarks. But we also know that the CP violation in quarks, in the quark sector, is too small to describe the matter dominance in the universe. So even though the effect is supposed to be small, the standard model CP violation is actually even compared to that, is too small to explain the effects required by the Sakharov condition. Now, this is an important bit because it's sometimes a little bit confusing. Discovery of CP violation with neutrinos, which is what we are trying to do here, would lend support to the leptogenesis model. But we also have to realize leptogenesis is going to happen at some large scale related to the energy scales after the Big Bang. One of the ways this could happen is through the decays of a heavy right-handed neutrino, which would be predicted in models which we call seesaw models. Now, the CP violation, if we measure the non-zero CP violation in neutrino physics, you still need a model to extrapolate this to the scales required for leptogenesis. I'll skip this slides because I'm going a little bit too slow, but it's not really relevant. So let me therefore now go to accelerators, which is the place where we can make these measurements for to look for CP violation. So the first thing we need is an artificial neutrino source. Mostly for what we have dealt with so far are natural neutrino sources. This is now different. We want a beam, and we have to produce the beam. And the problem is, of course, that neutrinos are very hard to control. The way this is usually done, you have a proton beam. In this case, this is 120 GeV at Fermilab from the main injector. And then these protons hit a target, a graphite target, for example, and produce secondary particles which contain a lot of stuff, but many of them are charged pions. These charged pions decay into muons and muon neutrinos, and the neutrinos from this decay we then use as a source of our beam. Now, one of the problems is to focus this neutrino beam, and one of the relevant and important contributions from CERN was to the invention of these magnetic horns by Simon van der Meer, which are basically tools to focus the charge pion in such a way that you can get a neutrino beam that is in some way focused. As always, these accelerator structures are complex. This is at Fermilab, and then of course it reminds of what happens at CERN. There is the former tevatron on this side, and then what's called the main injector, which is used to accelerate the protons, which hit then with 120 GeV these targets and produce in the two neutrino beams which currently exist at Fermilab. One is the NUMI beam, which goes to Sudan, and the other, which is used for the short wave line program, is the booster neutrino beam. This is just a photograph of Fermilab. That's the tevatron here, and this is the main injector, and the neutrinos go in that direction. So one of the problems with making a neutrino beam is again, it's not like a charged particle beam, which is easy to focus and create a monochromatic beam with a narrow energy spectrum. Just to understand this, what I've done here is this is the energy when I look at the pion decay at rest now of the neutrino that is produced when the pion decays at rest. That's about 30 MeV. And in order now to get the neutrino energies of the beam, we have to boost this into the lab system. We do this here with a gamma factor. And just to give you an idea, for a pion of 9 GeV at an angle of 0, you get a neutrino of about 3.8 GeV. However, this will depend, and you see that on this spectrum on the right, this will depend on the angle which you of the neutrinos, and you see the energy spectrum here for different angles with respect to the axis of 7 millirad, 14 and 21 millirad. Sorry, my mouse keeps disappearing. I don't know why. And you see, by going more and more off axis, we reduce the neutrino energy, but we also make it the distribution narrower and narrower. The other thing we can do, we can choose forward or reverse horn current. So by choosing the current in the horns, we can either produce neutrino or antineutrino beam, depending on whether we select the negatively or positively charged pions. And you see this for NOVA, one of the experiments at Fermilab. On the left is the neutrino mode. So you see it's mainly neutrino with a little bit of antineutrino and vice versa on the right. Now, if you want to build a long baseline experiment, what we have to do is to pick the location of the far detector in the most optimal place. And we do this by looking here. So this is the probability again for an initial muon neutrino beam to oscillate either into electrons or taus. We have seen this in a similar way before, and we have L over E in the bottom. And so if you look for the first oscillation maximum, this is here, and this is at an L over E of about 500 kilometers per GeV, and the second oscillation maximum is about at 1,700 kilometers per GeV. So, let's say we had a 1 GeV beam, we would choose our first detector location at 500 kilometers, our second detector location around 2,000 kilometers. We are not always totally free in the choice of location, obviously. And I choose two length scales here, which are fundamental for neutrino physics. No, they are not really fundamental for neutrino physics. They are more fundamental for geography. One of them is 300 kilometers. And this is basically the diameter of the island of Japan. And the bigger scale of 1,300 kilometers, well, that's what you can get in America when you go, it's a big country. When you go around Chicago, where the neutrino beam comes from, you will get on one side to the Rockies and in the north somewhere to Canada or Minnesota. Now, if we choose the first length scale, in order to get to 500 kilometers, we need, which was the first oscillation maximum, we need something like a beam energy of half a GeV. In that case, because it is such a short distance, and we'll probably not see any significant matter effects, and we'll be sensitive to the first oscillation maximum. To do that, and if I just remind you how it worked with a neutrino beam, where we select the neutrino energy by going off axis, what we do is we choose a narrow width neutrino beam by going off axis. If you go for the longer distance, we can actually pick two, the first and the second oscillation maximum, if we have energies of 0.8 and 2.5 GeV. We'll expect matter effects because it's much longer, and in order to be sensitive to the first and second oscillation maximum, we can use a broadband neutrino beam, and to do that, we go on axis where we don't select a particular energy. This has also impact, but this is more for tomorrow, on the reconstruction. At lower energies, you build more likely a Walter-Cherenkov detector. For higher energies, it makes more sense to build a liquid argon detector. So this is how the beams look like. This is the Japanese beam at the T2K beam, and you see it's located at 2.5, so their peak is roughly at the first oscillation maximum. On the right is the Dune beam, which is a function of energy, which is much broader, and you see it ranges from something like half a GeV to almost 5 or 6. Again, so what does that mean? Well, on the left, T2K, on the right, Dune, and you see the original beam spectrum, the flux, and then the curves, the oscillatory curves show the modulation of this, which you expect from the oscillations. And that's basically what we do as a measurement. So we measure at the near detector the flux, and then we measure the flux at the far detector, and we look at this oscillation. You see you're basically sensitive to the first maximum here, and here actually to at least 2. And then we compare these to this. These curves are just different values of the parameter set, and that's what we then fit. Now, in reality, the situation is, of course, more complicated because we don't actually measure event rates. We don't actually measure the flux, but we measure event rates. And this means, because we measure event rates, we become sensitive to other effects. We become sensitive to the cross sections, for example. If the cross sections are not constant as a function of energy, we have to understand exactly how that works. We often work in with nuclear targets. We also have to understand that. We also have to understand the detector response. And ideally, you would have the same detector, the near detector and the far detector, but that's not quite so easy. This integral, this ratio of integrals, which I shown here, given here, is basically expressing this in a mathematical form. What we do is we measure the ratio at the far and near detector as a function of energy, and that's a convolution of the flux, the probabilities for the oscillation, the cross section, some detector effects which describe this matrix. It describes the how your reconstructed energy and your true energy relate, and you have to do that in the far detector and the near detector. So it's a complicated story. I've shown something similar yesterday. So this is about the problem with the cross sections, because that's something we obviously have to understand. And again, on the left is just the flux of neutrinos, and on the right is the cross sections. But the typical region where we talk about for these experiments is in the GeV range. So the kind of processes we have to understand there are these. This is neutrino scattering on a nucleon. So this can be elastic scattering. It can be quasi-elastic scattering, which is shown here, where you turn the neutron into a proton. But it can also produce a delta resonance. All of these, of course, are weak interactions, which would produce like a pion and a proton. And that would be at roughly the mass of the delta resonance. And then you can have, if you go to high energies, what's called deep inelastic scattering, where you actually break up the proton and produce hadrons in the process. The processes that dominate as a function of energy, as I've shown on the previous slide, they change, and this is a compilation of muon neutrino data on nucleons taken from a publication by Sam Zeller and others. And there are a couple of things you see. This is for neutrinos and antineutrinos. The cross sections for antineutrinos are about a third of those for neutrinos. At higher energy, the deep inelastic scattering dominates in the middle, this delta resonance bit, and then quasi-elastic at the bottom. Now, this is the range of beam energies here, which we talked about. So this is the kind of processes we have to understand. And the other thing you see from this plot, which compares the data with with models, is that actually the data isn't that great. There's quite a lot of uncertainty on this, and this is a major problem for these experiments. I'll just quickly flash one experiment which does these measurements of neutrino cross sections. That's the Minerva experiment, and they just use a muon neutrino beam and have an active tracker target with a scintillator in them, and they can measure extremely well these kind of cross section, which is a very important bit for input for these kind of experiments. And I just flash these events because they show very nicely how they look like. This is in their detector. So here you see, for example, a quasi-elastic scattering event. That's a neutrino producing a proton, and the muon is coming out, which again you recognize by the length of the track. Then this is one where there's an anti-muon, and the neutron is visible here through something, like some light it produced, and it takes a while before it does that. There is a deep inelastic scattering event, which you can basically recognize. Here's the muon and a lot of other stuff that has been produced. And as I said, another complication here is that we have to understand nuclear effects, which are messy. So because most of these experiments work like, for example, Dune or with argon, or the scintillator experiments, you have carbon-like targets. So you have to understand that. it's a little bit different actually for hyper K or super K, of course, because here he worked with water, but still even in water, it's mainly a nuclear target. So you have a lot of effects which happen in the nucleus. What can happen is that things rescatter, and by these rescatterings, for example, what comes out of the nucleus doesn't look like what you expect. I actually did my thesis a long time ago on measuring of nuclear effects in deep inelastic scattering with muons, and turns out, this is it's a complicated business to understand this kind of stuff. So one thing you can do is you can measure with the same nucleus in your near detector and in your far detector, and this would, of course, potentially mitigate some of these effects. Now, these are the two operating long baseline experiments which do these kind of measurements, and I hope you understand now a little bit better why they are like this. So first here is Super Kamiokande on the right. So the baseline is about 300 kilometers from the one side of Japan to the other side of Japan. All these experiments, the far detectors are deep underground, and this is to get rid of cosmic rays which produce a major background. This is the T2K detector, sorry, the Super K detector, the water with the photomultipliers. We have had that before. And this is the near detector. And you see actually the near detector is a different technology from the far detector. So this is special about this experiment. The NOVA experiment has a baseline of 800 kilometers where the beam, the NUMI beam from Fermilab goes to Minnesota, and it actually uses scintillators, liquid scintillator, and has the same technology for far and near. This is again now a little more detailed T2K. The near detector comprises these calorimeters and also a beam monitor, which is called Ingrid. The Super Kamiokande detector is a Cherenkov detector with 50,000 tons of water surrounded by about 11,000 PMTs, large PMTs, 1 kilometers of rock above it to get rid of the cosmics. And just to give you the scale, it's about 40 meters in diameter and 40 meters in height. And of course, this is always true with all of these neutrino detectors because the cross sections are so small, we have to build very, very large detectors, which is, one of the challenges of neutrino physics. The way these neutrinos are detected, and we had this before yesterday, where they came from the atmosphere, and now they come from a beam, is through Cherenkov light, which produces a cone, which is characteristic of the speed of the particle, actually, and from which you can then derive its properties. This is two Cherenkov rings as recorded by this array of photomultipliers that surround the water. And one is a muon, one is an electron, and you might be able to guess which one is which. Well, it's not only the diameter, it's also of the ring, it's also the let me say, the fuzziness in the number of photons and how they are spread out, which is helping to identify. On the right is therefore an electron, and on the right and left is a muon ring. Of course, this is done in a more sophisticated way using algorithms. So the near detector, as I said, is quite different from the far detector. It contains ECALs, scintillator, and different types of detectors. So this is a challenge, but the main reason, of course, being that you cannot build a Cherenkov detector in the same form as a near detector. For the NOVA experiment, this is shown again here. You have two functionally identical tracking calorimeter detectors. The near detector is about 300 tons. The far detector is 14 kilotons, and it's on the surface. So this is going to be a challenge. Normally they would be underground, but here it's on the surface. And again, it's placed off axis to produce a narrow beam spectrum. And it currently has the longest baseline of any experiment. So this is what you get when you build a detector on the surface. All of this is cosmic rays. The way this is built, these are towers of these scintillators read out by APDs, and you just repeat this over and over again to build a very large volume. So you have to get rid of this cosmic stuff. And this is done very well, and it just shows you now a cleaned up interaction where the muon is here, and then there's the hadronic recoil there. Beautiful. Okay. Now, what's the bottom line? Of course, what we said, what we want to measure is what happens to the muon neutrino beam in these experiments. How many of the muon neutrinos we started out with actually disappeared, and how many electron neutrinos appeared. So this is the muon neutrino spectrum at the far detector measured by NOVA for the news and the anti-news left and right. And you see the spectrum compared to just one and quite a significant event sample of about 200 and 100 events with a very, very small background. This is from Neutrino 2020. This is the electron neutrino appearance. So what you see here, this is shown for different algorithms. So with different versions for the particle identification, and both for, again, neutrino and anti-neutrino beam. Now, the first thing you see that the number of events you see is much smaller than here for the muons, which is because electron appearance is a small effect. And it's also smaller in the anti-neutrino sample. Still, the sample is large enough to give like positive evidence for that this actually happens. You'll have some backgrounds a little more in here than for the muon neutrinos, but you know the signal is very clearly standing out. The T2K detector can do the same thing. Their energy distribution will look different, also because they reconstruct it in an entirely different way. Here again, this is the same plots you show muon neutrinos and anti-muon neutrinos for muon-like rings. And here for electron-like rings, you see the same pattern going back and forth. The electron neutrino appearance is a very small effect, and you get like whatever, 40 events or so, I guess, something like that. Just a reminder, how do we now extract the information from this? So this is we start with a muon neutrino beam, and then we look how many, we look for the muons here and the electrons here. That defines whether we have a muon neutrino or electron neutrino. This is the disappearance measurement. This is the appearance measurement. And now we fit all this. And this is how we extract the information. And it's a little more complicated than just counting the events. So we use the data samples in the near and the far detector. We use everything together, the flux model, the beam monitor data, hadron production data, cross-section models, detector models, the error correlation matrix, and then fit the oscillation parameters. And for some toy model, this is shown here, where you just have the data and different curves for different mixing angles. Now, to give you a flavor, quote unquote, that this is actually more complicated than it, than just the simpler equations I showed before. This is the probability for an electron neutrino appearance in the muon neutrino beam. And you see that it depends on all these factors, and it depends on this this is the number, this A is just proportional to the electron density in the matter it goes through. So this is this MSW effect. And then it depends on the various oscillation frequencies. And then, by the way, it also depends on delta, which is the number we want to extract. The thing is that because all this depends simultaneously on delta and the mass ordering, and of course also on these other parameters, which in parts we have determined through other experiments, you want to extract the data, the information simultaneously. This will work actually particularly well if our baseline is long and we have a lot of MSW effect, because then we can disentangle the effect of the mass ordering and of the CP violation phase. So let me end with showing you the bottom line of what the experiments that are currently running have measured. And they, of course, as always, plot this in a slightly different way. I'll give you a combined plot on the next slide. On the left is NOVA, on the right is T2K. They give the significance, or the delta chi-square, as a function of the delta CP parameter, which, of course, can be between 0 and 2 pi. Of course, if you had 0, then this would be kind of a trivial result. We wouldn't have any CP violation. What you see on the right, this is the T2K result. So this CP conservation, so 0 pi would be is excluded at the 90% confidence level by them, but of course that is still a relatively, I wouldn't say weak, but it still allows, of course, for almost anything to be possible. And there's a slight preference for normal ordering. On the left, you see the similar plot. Just note the different axes here. There's more sensitivity because of the longer baseline to the combination of CP phase and mass ordering, but they are difficult to disentangle. The normal ordering is slightly preferred. However, it's a 1 sigma effect, and they exclude inverted ordering at 3 sigma at this maximal delta, and disfavor normal ordering at 2 sigma at delta of 3 pi over half. If you put this all together, if this was slightly confusing, yeah, this is because it is all not very statistically significant yet. It's very exciting and interesting, but it's not, it's not at the 5 sigma level. And what the plot here shows as a function of this other mixing angle, which I haven't really talked about, the delta CP so this is NOVA and this is T2K, now shown on the same plot with the contours. And what you see here is that, well, the current data are pretty inconclusive. We expect some improvements with further running for these 2 experiments, but what you really need to disentangle this and to have unambiguous discovery of CP violation in the neutrino sector, you'll need the next generation of experiments that can do this at the 5 sigma level, and that's the thing I'll be talking about tomorrow.
All right, thanks, Stefan, and for very clear lecture. And I think we can have some questions. I saw already one question, I think, on the chat. I don't know if you see that.
Yeah, I see that. So basically, this is just so the question is, why is the beam narrow for the off-axis case? But this is just a kinematic effect. Yeah, this is just from the so you have to. This is just the kinematic effect from boosting this decay in the rest frame into the lab system, and you therefore basically you select from this Well, one way of looking at it is you see the on axis, by going off axis, you select slices of this, but of course the slices as you go on the to the left of this black curve will become narrower and narrower. But it's basically just a kinematic effect from this boost.
Right. Sohan has a question.
Sir, how do we calculate the gamma factor and the beta factor here in the formula?
Oh, this is just, I mean, you just calculate, this is from the energy and the mass of the pion. This is just, the 9GeV is just a particular number, which I picked because I picked one, but you know, you just calculate it from the, so the problem, of course, is that the protons come in with whatever, 120 GeV, let's say, in this case. But the pions that are being produced are not produced all collinearly, and they are not produced all with the same energy. So in order to really calculate the beam spectrum, you have to actually take the true distribution of pions which is produced in this process, and that's difficult. And that's, by the way, also one of the reasons why you can't just calculate analytically that, you know, you have to understand very well how all these things works, because it's not like a 9GeV beam. It's just one number which I picked from that distribution.
Okay, so the gamma factor is the normal relativistic factor. So it's, if you want to have a first estimate, it's just the energy divided by the mass, and then you have this 64. Balint.
Stefan, thanks a lot for this nice presentation. I had a question about cross-section, neutrino cross-sections. I understand the next generation of the Dune experiment is going to have the far detector liquid argon target. And we have a lot of understanding, well, more or less about the carbon and water. So I was just wondering, given the target sensitivities that one wants to reach for delta CP and so on, what is the current limitation in the understanding of neutrino cross-sections on argon target?
So in a way, you can see it already now from that plot. And of course, this is just the total cross section. The next problem is the whole interaction, the differential cross sections. Yeah, I mean, you don't only have to understand the total cross sections, but you also have to make measurements of the differential cross sections. One of the things which we can do to improve this understanding, which isn't very good yet, is to do these measurements at the Fermilab short baseline program, which would be Microboon, which is currently running, or SBND, which will be running in 22, or the third experiment is Icarus, which is also running. I think for the cross-section, it's really SBND and Microboon because they are the close experiments. They'll get enormous rates. The other thing you can do in Dune itself, and I'll mention this tomorrow, is there will be a liquid argon TPC, a pixel detector, and also a gas argon TPC. At least that's the plan. And the gas argon TPC is actually great to understand the interaction modeling because when you have the liquid, you absorb a lot of things, and in a gas argon TPC, you can actually measure the full interaction in a very nice way. Yeah?
Thanks.
All right. Any further questions? While you think, I have actually two more details which I saw. Can you go close by to slide 87? Just for the visual impression. So you have this showers and this detector in the back. Is this the actual size of what you would see in the detector geometrically to give that impression, or?
To be honest, I have just overlaid this without thinking about that bit.
Oh, okay.
I think it's probably not that far off, because if you look at the density of the TMTs, it is roughly comparable. Yeah.
Okay.
So I wouldn't say.
Yeah, that's what made me thinking, but in fact I never had thought about it. So all right, okay. And for slide 79, this is a micro detail, but you showed the Minerva experiment. And you said something like coming soon on this liquid helium targets. Is that still actually happening, or is that just a slide which was before they actually took that?
I had that slide for a couple of years, probably up.
Yeah, because I thought that's already done, but
yeah.
but okay, good, fine. Okay. Any other questions for today from anybody? I don't see anybody, anything now. Going once, twice. Okay. So thanks, Stefan. And we looking forward to another great lecture tomorrow, your third lecture on neutrino physics here.
Thank you.
And thanks, everybody. See you tomorrow. Bye.
Thank you. Bye.